Okay, well, look at a question here that asks us to explain how a vessel's still water rolling period is affected by changes in the distribution of weight aboard the vessel. Okay, well, I think if you were to look at the formula here, we can see that the rolling period, time in seconds, is 2 pi k over the square root of g times gm. So when we look at the formula, we can see that time in seconds is this here. 2 pi are constant, g 9.81 meters per second is constant, therefore the two variables are the letters k and gm. Gm, of course, is the GM of the vessel, so that will vary depending upon where weights are loaded vertically, and k is the radius of gyration, which will depend upon where the weights are in relation to the centre of the vessel, centre line of the vessel. So you can see there, just looking at the formula, that if the value of the radius of gyration, in other words the distance that the weight is from the centre line of the vessel dictates the radius of gyration, if that increases, if the weights are further from the centre and k increases, then the time in seconds for the rolling period is going to increase. Conversely, if the GM of the vessel, if you put the weights lower down, you've got a larger GM, then the rolling period is going to decrease. And when you think about it, if you're on a very stable vessel with a large GM, the rolling period is quicker. The vessel rolls a lot quicker. So that's looking at the formula and really explaining how the two interact. But when we look at what I've written here, or what's written here, the vertical distribution of weight will affect the GM. Lowering the weights will increase the GM, reducing the rolling period. And then we talk here about the distribution of weight about the rolling axis will affect the vessel's moment of inertia. And the moment of inertia is increased by winging out the weights. And what happens there with inertia that's created as the weights are winged out, the vessel will roll over until the inertia is the same as it is for the centre of the vessel, and therefore will bring the vessel back. So the distance of the weights from the centre of the vessel has a bearing on the inertia. So that's how you would explain that. Perhaps another way of thinking of it, for these tightrope walkers that hold a bar, so somebody walking across a tightrope, an individual walking across a tightrope, they actually hold onto a bar with weights at either end, and those weights, if you like, they're winging out the weights, and it means that if they're a little unsteady on the tightrope when they're walking over, because the weights are winged out, it allows them to wobble a little more either side instead of falling off. So it's all to do with the radius of gyration and the GM. And if we look at the formula, if you're unsure, just think to yourself mathematically what will happen if this is increased or this is increased, how it will affect this rolling period in seconds. Okay, the term synchronous rolling now we're talking about here, the dangers associated with it. Well, synchronism, this occurs when the natural period of roll is equal to the apparent period of wave. So when this occurs, the wave gives the ship a push each time she rolls, and therefore the roll becomes heavier and heavier, and it's known as synchronous rolling. Ship's natural period will be greater than the wave period, which rarely exceeds 10 seconds. So stiff ships with short periods of roll are likely to be more vulnerable to the beam sea, and container ship would be one example of that. The dangers, of course: capsize, cargo shift, structural damage, personal injury, and of course, as she rolls further and further, possible down flooding. The actions to be taken by the ship's officer if you are subject to synchronous rolling: alter course, ideally towards the waves, alter speed if the waves aren't on the beam, alter the vertical distribution of the weight, and alter the vertical and transverse distribution of the weight. And as we saw from the previous discussion about this, altering the weights, how the GM and the radius of gyration changes, it changes the inertia of the vessel, and therefore stops the synchronous rolling.